All right, so for the test, like I said, there's going to be 10 questions and a bonus. Here are the general topics, and like I said, these are not in order, okay? All right. Proof by induction. What's that? I'm sorry? No. I'm going to explain all these parts. Just let me get through the list, and then we'll go into it. All right. Quadratic-esque factoring, and we did that when doing a substitution so that it becomes a quadratic. No, I'll go into the. Yeah, like when you have to do a substitution to make it look like a quadratic, and then you can factor it. Okay. All right. There are pages in the book for all of these, and I'm going to give you pages to begin looking at these chapters and problems to look at, and we'll go through them one by one by one, all right? So, going backwards. Page 166, 1 through 5. Sequences and series is a bunch because we spent a long time on that. Page 59, 6 through 9. 62, page 62, 5 through 8. Page 70, 2 through 5. Excuse me. All right. I'm going to clean that up. And page 71, 5 through 8. I do not expect you to solve all these problems. I do not. I want you to look at them and say to yourself, can I do that? Do I know what to do there? If you don't, I'm giving you enough so that you can practice. Okay? That's all. There's way more in this list than anybody can do in any reasonable amount of time between now and the test. But I know that some of you are strong in some places and weak in others. And you are mature enough to be able to say to yourself, I'm good there, I'm not good there. All right? Complex numbers, page 182, 2 through 8. Compounded interest, page 63, 5 through 10. Exponentials, Page 87, 1 through 4. Logs. Page 108 through 110, all of them. Completing the square. Page 146 through page 148, all. Proof by induction. Where's that? Page 239, 3 through 5, and page 240, 6 through 9. And permutations and combinations, page 213. Oh, strike that. Sorry. That's when the chapter begins. I need to find a page for the binomial coefficients. I'll hopefully come up with that by the end of the block because I lost the page, and I'll come back to it. All right. Now, some of these, now you have to begin to think about what it's like for your teacher, because remember, and I'm not asking you to empathize with me, I'm asking you to think about how could I make a test, all right? I don't have 7 hours to test you. I don't. I only have the length of one block. And there are a lot of things in here, which means that I cannot give you a problem that will take 20 minutes. I don't have the time. So, you need to say to yourself, all right, how is he going to give me a proof by induction problem? Well, I'm certainly not going to give you something that will take you a long time. I'm not going to ask you to remember the verbiage, because that's just minutia. I'm not worried about that. But what I could ask would be, what's the missing step? Or, you know, I could give you a proof and have you fill in the gaps. Or say, what's wrong with this proof? Or something like that. Okay, so that if you understand induction, you'll be able to see what's wrong. But I'm not going to make you write out the full-on gory detail. That's just too much. Does that make sense? Now, something like compounded interest. You needed a calculator for those, right? I'm not going to have you sit there with a calculator. So how could I do it? I could say, set it up, and that's enough. Or solve for the amount of time, or solve for the rate, and something like that, where you would have to do algebra to get the expression for whatever it is that I'm looking for, and that's enough. So that if you did put it in a calculator, you would get the right answer. Everything up to the spot where you hit the enter key on the calculator. Okay? That's what I could ask you. So do not panic, but let's go through these, and I'll do examples. You can do examples, and let's make this file that I'm about to post at the end of the day, and this video, be a resource for you and for the two unlucky souls who are not here with us. Everybody say hi, Brian. Okay, everyone say hi, Austin. Get to class. Now, all right, so which one do you want to go through first? Okay, the quadratic-esque factoring. Wait, I didn't give a page number on that? Oops, sorry. That was page 86, my fault. 1 through 7. All right, everybody open up the book, or if you're Austin or Brian, you are at home playing with the PDF file that's posted on my Fusion page. All right. Page 86. Everyone go to page 86, and let's look at those numbers. Yeah. We have done this before. In fact, we've done all of this before. And realized that there's a lot of stuff on that page, right? So, you know, you've got some material to look at. All right. Now, quadratic-esque factoring. Somebody pick a problem and we will go through it. Great, number 4. All right, so simplify. Which one? Yeah, I think letter D is a good example. Let's do that. Page 86, number 4, letter D. So we need to simplify. All right. The first thing that I see is that I've got 20, and 20 is a product of 4 also. But I also see that I have both pieces to the same power. So let's go through this 2 different ways, perhaps. That's one way to play it. Right? Now, another way to play it would be this way. Giving you the same answer. Either way. That's one method. Now, this is not really quote-unquote factoring, and let's try and do one of those. So let's pick a problem that's perhaps a little bit more evil. 4G. Okay, let's write these down. Hold on. I got a request for 4G, and you said 7E. Let's do them both. All right, let's do 4G first. Please don't do that. Yeah, this was kind of like, I mean, these are kind of lightweight because these are just kind of like reminding us about the rules of exponentials. But the factoring ones, that's the ones that I'm more interested in. So let's look at 7E and see what that looks like. Ooh, there we go. That's fun. All right. That one's got some fangs and teeth. Fangs and claws. Sorry, fangs and claws. 25 to the x minus 23 to the 5x times 5 to the x minus 50 equals 0. All right, well, the first thing that I see is I've got 25 to the x, which is power 5. Sorry, it's got 5 to the x in it. So this is really 5 squared to the x, which, yeah, okay. And I'm just going to simplify. And this becomes, if I can, no, I'll write it again. Right? And we see that we've got a 5 to the x in 2 places. So let's make a substitution. So now we can turn this thing into a squared minus 23a minus 50 equaling 0. since this is a monic polynomial, monic polynomial is a coefficient of 1 on the first term, right? I don't have to stuff any rabbits, and I can straight factor. Right? And now we resubstitute, or rather we use the zero product property first. And now we resubstitute and solve for x. Now, we can immediately throw away the term on the right, the expression of the equation on the right, because there's no power of x, no real power of x, value of x that's going to give me a negative number. And now this becomes n x equals 2. So that's what I mean when I say quadratic-esque or quadratic-like factoring, okay? Now, I want to make sure that we have time to hit all of these topics today, so if it's okay, I'm going to leave it as this example. But if we have time at the end of the block and somebody wants me to go into another example, I'll be happy to, okay? Next, pick a topic. Sigma notation, good call. Go to page 66, 1 through 5. Yes. No. 2 times 3 times 11. 66. Oh, that was a typo. Oops. It's just plain old 66. 2 times 3 times 11. Okay. Yes.
You're gonna do it for like homework in the textbook, and then you'll give us a math problem in order to figure out which number we need to do.
No, don't give ideas.
That's a good idea.
What?
Ideas. Why?
I think it'd be interesting. What'd you say? Like, that gives us homework one day where like he gives us math problems to solve, and in order to know the numbers we need to do answer that problem.
That's a deal. But wasn't that? It's like.
The numbers in the problem would be related to the answers in the homework.
No, I was going more like you had to you gave us a math problem in order to figure out which numbers we needed to do.
I had thought about that actually, but I had found I thought about doing that for HL2 because I actually found problem numbers that I wanted to give them, and I found a generating function that if you plugged in 1 through 6, it would give you the problem numbers. And then I was like, I probably will get people not very happy about that one.
Well, you could
But
always give only,
you never know.
3 homework problems.
This is true. Find, do the problems that are the solutions to the function. Right. All right, so pick one on page 66.
How about 4A?
Okay.
Yes, yeah. How about 4C?
How about 5B?
Okay.
Okay, go good.
Yeah, that's good. Yeah, it'll help us.
All right, so I know that the sum of k is equal, and this is n k equals 1, and this is just restating the problem. And I also know and we are asked to find the simplest form of k plus 1 times k plus 2. All right, so the first thing I'm going to do is I'm going to multiply out k plus 1 times k plus 2 and see exactly what the heck it is I'm dealing with. And that becomes k squared plus 3k plus 3. Right? Plus 2. Wow. Yeah, the multiplication thing. Wow. Yeah. So now, using the properties of sigma notation, I can split this guy up. And now, using the properties of sigma notation, I can do just a tiny little bit more. Well, first of all, I know what this guy's equal to, this first term. That's equal to the second term over here, right? And now this fellow is simplified to be him. And this last term, well, this is just a whole bunch of 2's, isn't it? It's just, and how many 2's are there? N of them, right? That's given to me in the beginning of the problem. I know these two facts, right? That the sum of n k terms is this, and then the sum of n k squared terms is that. Those were given to me at the beginning of the problem. Which term? Huh? I haven't done. I'm not finished. So, what was the question? Stand up here and or point to it, because I don't know what you're saying. Just point to it. I'm not done with it. I'm not finished. The second, she pointed to this term. Right, because if you think about it, it's 3 times a number plus 3 times a number plus 3 times a number plus 3 times a number. So every term is multiplied by 3, right? So I could factor out a GCD. Here, let's... Right? Everybody has a 3, so I pull out a 3. Which is, now this is the sum of my k's, right? So if I have a constant, I can pull a constant out in front of a sigma notation. That was one of the properties of sigma notations. Constants can get factored out. As long as these things don't contain k, which changes each time, then I can pull out a constant. So now I have
Plus 1 plus second compared to 7 first.
which one? Point to it. I don't know what you're talking about.
I thought this was 2n.
Is it?
That's what this was.
Does, or did I give myself a typo? It's 2n plus 1. Yeah. Thank you. I made myself a typo. And now I can combine all my like terms, get common denominators and all sorts of such things. And this is going to get a little ugly, but it's not going to be the end of the world. And that's it. Sure. Yeah, that helps. I'm lost. I've gone to go find myself. If I should return before I get back, please tell me to wait. All right. That's probably the meat of it. The rest is just algebra combining like terms and whatnot, multiplying out, and the rest is algebra. But that's where the meat of the whole problem is. So this problem illustrated the properties of sigma notation. First, that you can pull out a constant. Oh, sorry. First, that you can break up a sum into separate sigma notations. And second, that you can pull a constant out in front. All right. There is one other property of sigma notation that we saw when we were playing around with induction, and it's worth noting. If I can move past this slide. Almost. Do you remember the last homework assignment on induction where we had to increase the number above the sigma notation by 1? We had to go from the k term to the k plus 1 term. That property is an important property. It was at 9 and 12, right? Yeah, that's why it became 22. And in 21. No, it's fine. It's okay. I'm going to skip the next part of this problem, which says find the first 10 terms or something. Find the sum of the first 10 terms. Okay. Well, yeah, I mean, you would have, the problem, you know, number 5, part B contains check your answer in the case when n equals 10, which I'm not about to do. And that's the final honest to God answer. Because I've factored out a 2 and simplified. Sure. No problem. This property is important. I should just say, maybe not that, but so I have something in there, a of k. I mean, you know, it could be k squared plus 7, or, you know, k divided by 5 to the k, or whatever the heck it is. It doesn't matter. But if I wanted to turn this into, if I needed to change that, right? I would add, for example, the next term up, which would be k plus 1. This is an important problem. Yes, sir. In that case, we would have to add from from the k plus 1 term, and we would have to add all of those terms up to 2k. For example, let me do a real honest to God example, and then maybe this will become less abstract. All right, and I wanted to change that, maybe not 4. Let's not use 4. 3. Okay, I just didn't want us to get confused with what 4 am I talking about. I wanted to change that 4 into a 5. All right. Well, let's first blow this thing up and see what it looks like, so that we can put our brain about what it would look like if it really was a 5. Okay. This is 1 all over 3 to the first, 2 all over 3 to the second, 3 all over 3 to the third, and 4 over 3 to the fourth. That's what he looks like right now. All right. Imagine what it would look like if it really was a 5 on the top. It would look the same, except there would be another term at the end, which would be 5 over 3 to the fifth. Okay. That's what it would look like. So if I wanted to turn that 4 into a 5, all I have to do is take what I've got and add one more term to it, and I'll get what I'm looking for. So if I do 5 all over 3 to the fifth plus my sigma notation, you see, now what I've got but now I've added, and I'm going to see if I can give myself some room here. You see, I've artificially added, well, not artificially, but I have added both of these terms. And now what this whole thing looks like is okay? So that's how you can change a bound. if you need to. All right? And this was kind of at the crux of the sigma notation induction problems. All right? Okay, and let's generalize it and say that this is if that is a to the k, the kth term, whatever k is, then this guy here on the left is the a to the k plus 1 term. It's the next term down the line. All right? Actually, I shouldn't say k plus 1. It's n plus 1. Let's fix my notes. Okay, so this is a nice tool for you to use to change the bounds should you need to. Okay? Happy? Wonderful. All right, next problem type. Sir? Like what?
Like with the structure of functions, like search action.
No. That was painful enough. And we didn't get through the unit, so I'm not going to test on it, Well, if you count the number of topics that are on that list, how many are there? 11.
That's not nice.
So one of them will be a bonus.
Oh.
Binomial coefficients. Okay. All right. Next one you want to talk about?
Binomial coefficients. Sure.
Actually,
For what? Which ones? Completing the square is actually considered prior knowledge, but it's such a useful tool. It's such a useful tool, and it's used in all sorts of places that it's worth doing. And also, it's a tool that is necessary for solving some of the complex number problems. Hint, hint. Now, which one did you want to do next? You said binomial expansion?
I said lost this.
All right.
Let's. Good. I like logs.
All right, let's do logs. Logs was 108 through 110 all. Pick one. Great, number 3E. Good call. I would have picked that one too. All right, so page 108. Oh, and by the way, you will be getting the IB formula sheet.
Will it help us?
It might. Okay, I'll be posting it on the Fusion page so you can look at it. It's a beast. I think it's like 15 pages long. But I will have paper copies for you to take on the test, so you don't have to print it yourself. It will be the full-on beast, which you should probably keep, okay, as a reference for ever.
Does anyone have interest in the series?
It has sequences and series on it. I'm not sure. I'd have to look. But if it's available to you on the IB test, so it's going to be available to you on my tests.
Regardless of whether or not it will help us.
You never know what'll spark your memory. I don't know, right? So this is page 108, 3A. No, 3E. That's the one that all of you wanted, right?
It's a scary.
This is log 25. Log 0.2. All right, so what is the log? What is the base of these logs? 10, because it's not written, so it's assumed to be 10. All right. Now, if you were to go ahead and do the change of base formula right now, this would equal log base 0.2 of 25. Correct? Not so nice and not complete. We could actually get a numeric value for this beast, and we're going to. So let's first attack the log 0.2 bit and see what happens with that. Yeah, it becomes 1/5. Right, so let's look at this for a moment. And log base anything of 1 is 0. Very good. Right? So just plain old negative log of base 5. So this one not complete. So let's go and solve and simplify this a little bit more. So I have log base 20 of 25 all over negative log of 5, which equals the log base 5. Actually, let's first let's not confuse ourselves. Okay, I just wanted to pull that negative sign out because it wasn't part of the definition of the change of base formula. Okay, so that we don't get wrapped up in a negative sign. Okay, and now we can go a little further. Done.
Would it help to change the base if you did the division like you did before?
The division rule for log states if I have log of A minus log of B, this is equal to the log of A over B, not log of B, log of A over B. This was one of the ones that was, fix the problems with the logs, right? And I actually have my answer key to that, and I'll post it on my Fusion page also, so you can see common error answers. Okay, I'll post that as well. That's done. All right. Next, where do we want to go? For B, show that log square root of 2 is equal to 1/2 log of 2.
Oh, no, wait, I get that.
Yeah, I got that.
How about 5e, not 5f?
5f. Log base B of 0.2 bar. This is a good problem because it goes back to how to write a repeating decimal as a fraction. Log base B of 0.2 bar. Well, remember, 0.2 bar, that's equal to 2/9. Okay. That's the repeating decimal trick, right?
It's like 0.235 or
0.235 would be 235 over 999.
Okay.
Right?
So then like 313.
it's the length of the reptend, which is the number of digits that are repeated, okay, over that many 9s. So if you have 0.313313, right? Right? That's equal to that. Now, of course, you can simplify that. No, you can't. But sometimes you can, right? It's a nice trick. Actually, no, wait. So this becomes and you're done.
Well, couldn't you put take 9, make it 3 squared, focus to that?
You could do that. And there's nothing wrong with that. Sometimes it's useful, sometimes it's not. This you could. I wouldn't say it's wrong or anything. That's fine. Yeah, I would accept that, or I would accept that, and those are just fine with me. Since, you know, I mean, if you knew B, maybe one of these would be preferable because it might simplify, or something like that, you know? I mean, if you were dealing with a base of 3, or a base of 2, right? Or even maybe a base of 6, you know, that might be able to play. Let's do something from the next exercise, perhaps. Exercise 4C.2, which is like page 109 stuff. A pick.
Or what do you think will best help us?
All right, well, let's do one from each group. There's only 3 there, 1, 2, and 3, right? Let's, how about, okay, how about, I don't have any R's. How about this? I have AJ, Charlie, and Eric, so I'll do an A, a C, and an E. Okay. 1A. This is page what, 109? Y equals 2 to the x. And you're supposed to be writing this as a logarithmic expression, right? As a logarithm equation. Now, at this point, you could use any base log you like. I don't care. You could do 2, you could do 10, you could do anything. I don't care. Don't pick something really goofy because that's probably not going to be nice. But let's just do log base 2 of y equals log base 2 of 2 to the x, which equals x log base 2 of 2. You could always just go straight to the first rule of logs, which would give you the same answer. But this was kind of it in full-on gory detail, or, you know, all of its glory right there. So let's do another one. To C. Is it a half? Oh, I'm sorry. Yeah, that's what it says. Sure. Yeah. Yeah. Okay. Okay. Now, sometimes A is 1, a lot of times it's 1. But if it's not 1, that's what it is. That's how you play with it. Okay. That's where it goes. And 3E. That's a good one. Oh, sorry. Rule 7. Gives me because it's the base. I mean, if those were logs to the base of 3, we would jack a 3 under both sides, and then they would fall apart. But if you think about it, a logarithm is just an operator, and if I mean, it's some sort of, meat grinder that I throw p into, and when I throw the square root of x into that same meat grinder, I get the same thing out. So that means that p and the square root of x has to be the same thing. Okay.
Oh.
All right, so 3E. Fluffy, what's going on, man? All right, so this, huh?
I was thinking, is it x times log of base 1, or log 1?
Say that again.
Do the x plus 1 effectively multiplies, isn't it?
Is what multiplying?
Sorry, the second step.
Yes.
So in that way, 0.
I can't break up an addition. Logarithm does not distribute over addition. Logarithms don't distribute at all. Okay. Now, you should always go and check your extraneous solutions with logs, okay? Because logs are not surjective, I believe, the one that I always mess them up. But it's not found in all the domain. I mean, not every x is good to plug into a log. And in fact, if we look here, if I take the log of -6, it's undefined in the real numbers. So this is out. Oh, you're here. Great. Hold on one second. Oh, yeah, just put that on my desk. That's fine. All right, so we're going over problems. Here, give him one of those books. Yeah, we're going over sample problems that will hopefully prepare you for the test. Okay, and at the beginning of this video, which you should watch, there's a list of page numbers and problem numbers for all the topics that we've covered. So if you feel strong about something, that's fine. You don't have to worry about it. But if you're feeling weak on a particular topic, you should work those. Okay? You're fine. All right, so yeah, this video will be posted by the end of the day. All right, so those were our log problems. What's next?
Nothing else I'm asking.
Let's do exponentials.
Well, exponentials are always the square root.
Is that 87 or 187? Hold on.
Do some induction.
Okay, let's talk about the induction stuff. Like I said, I'm not going to have you do a full-blown out induction, but I could easily have you solve or prove a base case, or I could have you fill in the missing step. I'm not going to ask you to memorize verbiage. It's not the purpose of what I'm interested in. But let's go and look at those problem numbers. Which one did we say it was? 239 and 240. Let's look at those. 239 and 240. All right, 239, I said 3 through 5. Pick one. 4B, okay. Prove the following propositions are true for n of the element of the positive integers. So, I'm going to simplify the writing on all of this to say, not n, let's use k. All right. That one's a little nasty. So let's first test the base case and see if it actually flies. Okay. So the base case would be what? 2, right? So and let's attack the right. Is this right? Did I copy it wrong? Oh, no, wait, I forgot the numerators. Ooh, that would help. Huh. Yeah, it would be k minus 1, wouldn't it? No, n is where it ends. K is the thing that changes. So if you look at those terms, it's 2 over 3 factorial, 3 over 4 factorial, right? So this becomes 2 minus 1, which is 1/2. All right, and now I wind up with playing with this, which is 5 all over 6, which is not the same. Base case fails. Done. Wait, am I right? Hold on one second. No. 4 over 5 factorial. Well, okay, where's the error, guys? Where's the error? I don't see it yet.
Okay, so like back and forth.
Hold on. 1/2 factorial plus 2/3 factorial plus 3/4 factorial. So if I just go right in here and plug in 2. Oh, no, wait. It would have to be 1. We have to rewrite this term in order for it to be 1. Because that's actually for 2. This would be k all over k plus 1 factorial. That's how we have to write it. Because k has to start at 1 because it says it's true for all positive integers. Right? Yeah. So now this becomes, for the base case, I get 1 all over 1 plus 1 factorial, which is 1 all over 2 factorial, which is 1/2. And now this, at case of 1, becomes 2 factorial minus 1 all over 2 factorial, which is 2 minus 1 all over 2, which is 1/2. So the base case holds. No, I just changed how I wrote my summation so that I would incorporate the first term. You see, if you look at the terms on that page, they start off with 1/2 factorial, 2/3 factorial. And it says specifically that it's true for all positive integers. So I have to include 1. All right, and now we assume the base case holds. Oh, sorry, it holds for all n up to some term j. And now I have to prove the j plus 1 case, which is of the form. It looks like j plus 1 factorial minus 1 all over j plus 1 plus 1 factorial. That's what we're looking for. To do that, we begin with the assumption, which is j plus 1 factorial minus 1 all over j plus 1 factorial is what it looks like, and then this becomes so I'm going to change my bounds on the left by adding the j plus 1 term, which would look like this is what we covered a minute ago. So all I did was I added the j plus 1 term to both sides, which changed the bounds. And now we got to figure out what all this mess is, right? All right, so let's look at this a little bit further and realize I've got j plus 1 all over j plus 2 factorial plus j plus 1 factorial minus 1 all over j plus 1 factorial. Right? Great. Now, yuck, but not impossible. Yes, you can. Agreed? Question?
Yeah, I would say.
Yeah, I don't want to spend all day on this problem.
Okay.
Okay, moving on. Thank you. So now I have, and like I said, you're not going to have to do this on the test. So we're kind of wasting our time, but done. Thank you. I'll be here till June. All right. Next problem. Okay. Huh? Okay. We only have 10 minutes left of class, so I want to make sure that I hit another hot button issue if anybody has another topic you want to talk about.
Can we practice the sequences in series?
Sequences in series. All right. So the reason why I gave you 4 sets of problems for sequences in series is because the way the book breaks it up is like finding the nth term, or find the first term that's above 1,000,000 or something like that, right? And then they say, and then there are other ones that are find the sum of these series. So there's arithmetic and geometric, nth term and sum. Okay. So those formulas, I gave you this list a while ago, but arithmetic, geometric, nth, sum, right? Okay, so if I want the nth term of an arithmetic sequence, if I want the nth term of a geometric sequence, I'm thinking of the sum. Whoops. If I want the sum of an arithmetic sequence, I should just say set. That is Dane Bramage. Yes, n times n plus 1 all over 2, and then sum of a geometric some of the geometric terms. This is G1, 1 minus r to the n, all over 1 minus r. However, if I had an infinite one, lied. Question. These are on the formula sheet.
Oh, really?
You how to use them isn't, but what they look like, yes. Sir.
Okay, for the, like, you looked at the sum of the comparison. Yeah. Yeah, it does.
It is.
My notes is I got n over 2
Mhm.
times a1 plus an.
Oh, I got it. I'm confusing myself with the sums that we did a minute before. The first plus the last times n over 2. Yeah.
There was like something about different ways to put like, the equations. There was like a. I can't remember. Yeah. You know what I'm talking about? Do you know the word
That makes
for it?
2 of you, because I don't know what you're talking about.
It's one.
Oh, yeah. There was another form. That's basically plugging one formula into the other, and let me go back and look. Plugging this a to the n in here, right? That's basically how you get it. And now it becomes n over 2. This is a1 plus a to the n, and now we substitute right in here. Right? That's me substituting it in, and now I'm going to distribute and combine and do all that lovely stuff, and I wind up with yeah, this one doesn't have the last term in it.
Right.
You know, so if you don't have the last term, this is the one to use. So that's in there too. I'm not sure if the IB formula sheet has them both. It probably does. If it doesn't, you can derive it yourself. You just plug one into the other like I just did. Okay. Still have about 4 more minutes, so if anybody has any questions. No, you do not need to do that. That. Fun. All right. Any other questions?
Back. Explicit recursive.
Yeah.
Oh,
The top one or the bottom one? Yeah. I'm not sure if it's on the formula sheet or not, but it's one that I'll post the formula sheet so you can look at it and see. If it's not, it's one that you should know. But all you need is the ones that are, and you can derive it like I did. Oh, explicit and recursive. Okay. All right, this is explicit. What I'm looking at right here is explicit. Okay. A recursive has 2 parts. So if I have terms that go right, okay, then I would say A1 equals 5, and the n, you have to have this one. You have to have a starting place. If you don't have a starting place, then I don't know where to begin. You're just saying, hey, add 2. Add 2 to what? You know, add 2 to the term before it. Well, what's the term before it? I don't know where to begin. You see? So that's how you would write it. That's the recursive form. And the explicit form for this particular one would be to find the nth term. That's A1 using the formula. Well, for this guy, my difference is 2. So this one has to have both parts. And that's the recursive above and the explicit below. Explicit just says, hey, what term do you want? You want the 50th term? Here you go. Boom. There it is. If the recursive says, you want the 50th term? Wait a minute while I sit here and figure out what the 1 through 49th term is. You know, I got to go 5, 7, 9, 11, 13, blah, 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 all the way up to the 49th so that I can add 2 to it to get the 50th. You see what I mean? But sometimes the recursive is the nice way to go because the explicit can be difficult. It might not be a simple arithmetic or geometric one. Okay? You know, if there are, like for example, the Fibonacci sequence. There are explicit formulas for the Fibonacci sequence. But if you didn't know them, the only way that you could do it would be to go and add up the 2 terms before it. All right, this episode of The Ronco Show has been brought to you by the entire first quarter of class.